Hi everyone, today a video on alcohols and specifically the reactions of alcohols. So the sort of simplest reaction we can think of for this is combustion to start with. Alcohols will burn completely if it's complete combustion, there's enough oxygen to produce carbon dioxide and water. Remember, those are the two combustion products that we always get in complete combustion. So the example at the bottom is ethanol reacting with oxygen in complete combustion to give carbon dioxide and water. And remember that we have to balance our equations. The simplest way to do these is to balance the carbons first, since carbon is only present in the alcohol and carbon dioxide, so it's very easy to balance those first, and then to balance the oxygen and hydrogen atoms last. If it's incomplete combustion, i.e. there's not enough oxygen available, well then carbon monoxide, CO, or even just carbon, soot, essentially can be produced. So the combustion is normally complete oxidation, but alcohols can be also oxidized gently and in stages. And so if we consider starting with a primary alcohol, ethanol, i.e. the carbon that the OH is attached to is only attached to one other carbon group, we can oxidize this first of all up to something called ethanal, which is an aldehyde. Aldehydes are characterized by having a CO double bond and a hydrogen attached to that unsaturated carbon. And we can also continue to oxidize it up to something called ethanoic acid, which is a carboxylic acid. And this is characterized by having a carbon atom doubly bonded to an oxygen and an OH group bounded to the same carbon. So an aldehyde can often be written down as RCHO. Note the distinction, not RCOH, because that's an alcohol, RCHO. And carboxylic acids can be written as RCOOH. Now, if we take a secondary alcohol, we can also oxidize that. So, for example, here, propan-2-ol can be oxidized. And you can see the same sort of thing happens that we've turned that COH single bond into a C double bond O. So this is now called propanone. This is a ketone. Now, a ketone is characterized by having a CO double bond, then with carbon groups attached as well. So the difference between an aldehyde and a ketone is that an aldehyde has a hydrogen atom attached and a carbon group attached to the C double bonded O group. A ketone has the C double bonded O group and two carbon-based groups attached. Now notice that we can't go any further than that. Secondary alcohols can only be oxidized up to the ketone. They can't go any further. The reason why they can't go any further is, remember the definition of oxidation. We can think of oxidation as being the addition of oxygen or the removal of hydrogen. And so in order for these reactions to work, if we go back to our ethanol going to ethanal, you'll see on that second carbon that for that to happen, what's had to happen is we've removed a hydrogen atom. Likewise, in then going from ethanal to ethanoic acid, in that case we've added our oxygen in, the CH has become a COH. For propan-2-ol, well, we can take the hydrogen atom off that central carbon to make it into propanone, but then there's no more hydrogen atoms left on that carbon. And so we cannot oxidize any further. And the reason is because to do oxidation any further, we'd have to break a carbon-carbon bond now rather than a carbon-hydrogen bond. Now, typically carbon-carbon bonds are actually a little bit less strong than carbon-hydrogen bonds. So it's not to do with strength, it's more to do with reactivity. If you look into the mechanism, which is beyond A-level standard, really, you'll see that actually it needs to be able to attack a hydrogen atom rather than a carbon atom. And tertiary alcohols are not easily oxidized for the same reason. A tertiary alcohol has three carbon groups attached to that COH part of it. To oxidize that, we'd have to break, again, a carbon-carbon bond, which is not easily done. So the take-home message is that primary alcohols are oxidized up to aldehydes, which can be further oxidized up to carboxylic acids. And the way that we can control this, or one of the ways we can control it, is the conditions which we do the oxidation. If we do the oxidation where the alcohol is in excess under a distillation apparatus, then that's ethanol to ethanal, the production of the aldehyde. If we oxidize our alcohol or our aldehyde using our oxidizing agent, this O in brackets, in excess, and we do it under reflux, then we produce the carboxylic acid. And we'll see on another slide some of the practical details. Secondary alcohols get oxidized to propanone, and typically that's done under reflux. we don't have to worry so much about conditions because that's the only product we can get. And tertiary alcohols aren't easily oxidized. So the experimental details, the oxidizing agent that we use is called potassium dichromate that we acidify with dilute sulfuric acid. Now, there's a few ways of writing this. Of course, sulfuric acid is H2SO4, but we can also just write it as H+. And the potassium dichromate has the formula K2Cr2O7. Remember that potassium is a 1+ cation, and so the Cr2O7 has an overall charge of 2-. It's something called the dichromate anion. So we can either write it as kind of a full expression, H2SO4/K2Cr2O7, or as a slightly simplified ionic expression as H+ Cr2O7 2-. It doesn't really matter which way you write it down as long as you're consistent in the way that you write it down. Now, in our dichromate anion, our Cr2O7 2-, the chromium is actually in a +6 state. It's chromium 6+. And these ions are orange coloured. Now, when we oxidize up our alcohol, let's say we go from an alcohol to an aldehyde, ethanol to ethanal, we've oxidized our alcohol, and so our oxidizing agent, because remember the oxidation and reduction reactions must happen together, redox, the oxidizing agent has to end up being reduced. So our chromium 6+ is reduced to chromium 3+. Remember that reduction is the gain of electrons. And so this is very useful colour change to know if it's worked, because chromium 6 is orange, chromium 3 is green. So if it asks you for the colour change in one of these oxidation reactions, it is orange to green. So to oxidize ethanol to ethanal, that's the alcohol to the aldehyde, we use dilute acid and less oxidizing agent than we need for complete oxidation. Essentially, we have the alcohol in excess, and the mixture is heated using distillation apparatus. Now, the reason for this is because we don't want to go the full way to oxidizing it to the carboxylic acid. We want to be able to stop at the aldehyde. So by using excess alcohol, that's one way that we can do it. The other way is the distillation, and this really is the key part of it. Ethanal has a lower boiling point than ethanol. It's lost that hydrogen bonding ability. So it has less intermolecular forces, and therefore a lower boiling point. And so the ethanal vaporizes as soon as it's formed and can be distilled off. So you get rid of it, you take it away from the oxidizing agent before it has a chance to kind of continue oxidizing. And over on the right, you can see the sort of practical setup. We have a pear-shaped flask with our oxidizing agent and our alcohol in. We're heating it. Thermometer placed in the top so we can monitor the temperature. What we want to actually be monitoring is the temperature of the vapors at the top. We don't want to be sticking the thermometer straight down into the temperature of the solution, but we want what the temperature is of the vapors at the kind of neck of that apparatus. We then have our condenser that we've attached with water in at the bottom of it, water out at the top. This creates a cooling jacket essentially, and it allows the aldehyde, the ethanal, as soon as it vaporizes, to be collected at the top, cooled down, and collected as a distilled product. If we wanted to go the full way to oxidize the ethanol to ethanoic acid, we now use concentrated acid and enough oxidizing agent for a complete oxidation, i.e. we put the oxidizing agent in excess. It means that we're going to oxidize absolutely all of our alcohol. And the key experimental detail is that we reflux the mixture now rather than distill it. So in distilling it, we heat it. As soon as the thing with the lower boiling point forms, it's collected in that cooling apparatus in the condenser, and condenses and is taken away straight away. In reflux, we heat our sample. We have our condenser placed directly above, again water in at the bottom and water out at the top. And what it means is that we heat our solution continuously. Now we could do it without this condenser on the top. We could just heat our flask. But of course, as the carboxylic acid forms, as the aldehyde forms, as these things become vapors, if there's nothing at the top to stop them escaping, well, they'll just escape. and we'll end up losing lots of product. Our yield will be reduced. So what the condenser does at the top is it allows the vapours to go up into the condenser and then be condensed back down to liquid and fall back into the flask. And what this means is that you can continuously oxidize your alcohol. If you end up forming some aldehyde that vaporizes, it will go up to the condenser, cool back down, condense back into the flask, and it can be reoxidized back up to the carboxylic acid. So it allows us to continually heat something without loss, without significant loss of any of our product, without dropping our yield down. So distillation can then be used at the end of this, once we've heated it for long enough and made sure that we have our carboxylic acid. We can then use distillation to separate that acid product out. We can also write some equations, and typically rather than using the full formula of the oxidizing agent because it's a bit complex, we just tend to use O in square brackets to denote an oxidizing agent. So when we're oxidizing our ethanol to ethanal, the aldehyde, we have CH3CH2OH plus our oxidizing agent. And remember that our aldehydes are characterized by a CHO functional group, so it's CH3CHO, and we produce water. To oxidize the ethanol to the ethanoic acid, similar idea, CH3CH2OH plus 2 lots of oxidizing agent. This is why we tend to have the oxidizing agent in excess, to produce CH3COOH. Remember that the COOH group is the characteristic carboxylic acid, and water. So just to recap, our aldehydes and our ketones, our aldehyde is an R-CHO group, our ketone is an R2-CO group. So they both have this CO double bond, but an aldehyde has one R group, one hydrogen group. Ketone has 2 R groups attached. And so we name aldehydes with the suffix -al, for example, ethanal, and we name ketones with the suffix -one, such as propanone. And the carbon that's in this carbonyl group, this CO group, we count in the chain. Now we can also do some tests that will allow us to distinguish between whether we have an aldehyde or a ketone. Now, aldehydes and ketones have very similar chemical properties, but the key difference, as we've seen before, is that aldehydes can be further oxidized to carboxylic acids. Ketones can't be, because we'd have to break a carbon-carbon bond rather than a carbon-hydrogen bond. And so there are 2 reagents that we can use for this. The first is the Tollens reagent. It's called the Tollens silver mirror test. And this is a solution of silver nitrate in aqueous ammonia. Essentially what this ends up forming is this silver diamine complex ion, AgNH3 2+. Now what this will do, because the aldehydes can be oxidized further, it will oxidize the aldehydes, but it won't affect ketones. And so the reaction that occurs is by the reagent oxidizing your aldehyde up to the carboxylic acid, the reagent itself must get reduced, because remember, redox, they have to happen at the same time, reduction and oxidation. So the aldehyde is oxidized, and our Tollens reagents get reduced, and we end up producing just metallic silver. And so what you'll see on the, if you do this in a test tube, you can see the picture on the right, is we start off with a colourless solution, and you'll end up forming literally metallic silver around the edges of your test tube. So it's a very, very clear test to see whether you have an aldehyde. The other one is Fehling's or Benedict's reagents. Both of these are reagents that are oxidizing agents that contain a blue copper-2 complex ion. And these will again oxidize the aldehydes up to the carboxylic acids, but they will not be able to oxidize ketones. And so again, we oxidize our aldehyde to the carboxylic acid, and so our reagent, in this case the copper, must get reduced, and so we go from having copper hydroxide, copper 2, down to copper oxide, copper 1. And these copper ions are very different colours, so on warming an aldehyde with either of these reagents, the blue solution of the copper hydroxide gradually changes to a brick red precipitate of copper 1 oxide. So the key takeaway messages is that you can use Tollens reagent, which for aldehydes will give you a silver mirror. For ketones, it'll be still a colourless solution, no change. If you use Fehling's or Benedict solutions, You'll start off with a blue solution, and if it's an aldehyde, it will turn into a brick red precipitate. If it was a ketone, you'd stick with the blue solution. The other type of reaction that we have for alcohols that we need to know about is something called an elimination reaction. So this is a reaction where a small molecule is literally removed, literally eliminated from a molecule. Now for alcohols, this molecule is always water, and the water is made from the OH group of the alcohol and an H atom from somewhere else, typically an acid in the solution. And these elimination reactions of alcohols, because we lose water, they're called a dehydration reaction. And the product of this is always an alkene. Now the key thing for an elimination reaction to occur is there must be a CH bond on the carbon that is next to the carbon that contains the OH group. So let's have a look at the mechanism. We typically do this reaction by using excess hot concentrated sulfuric acid. We pass the vapours over a heated aluminium oxide solid catalyst, and it's sometimes in the presence of phosphoric acid. So you can either use the sort of sulfuric acid or the phosphoric acid, but you need some acid in there. And the reason for that is because the first step of this reaction is to protonate the OH group on the alcohol. So our alcohol, the OH bit of it, has lone pairs, acts as a nucleophile. Our H plus is our typical electrophile, and so we can draw our arrow from a lone pair to the H plus. This now creates an OH2 group, which is positively charged. Remember that our mechanisms have to balance in terms of atoms and in terms of charge. So we've started off with a positive charge overall. We have to have a positive charge in this molecule, and it goes on to the oxygen because the oxygen has 3 bonds. And this bit is the elimination of the water. We call it the acid-catalyzed dehydration or the acid-catalyzed elimination of water. And so our arrow is very simply an arrow that goes from the CO bond, that's our electron density region, to ending up on the electronegative oxygen. This loses water, and now as we've kicked off something from that carbon atom, well, the carbon atom now doesn't have the maximum number of bonds, it only has 3 bonds, and so we've created a carbocation. Again, remember the charge has to balance. We've kicked off H2O, a neutral molecule, so the positive charge remains somewhere in this molecule, and it's on the carbon that we've lost the OH group from. So this is our carbocation. Remember that carbocations are planar species. Then that's not a stable arrangement. The carbocation is an intermediate and then stable, and so to get to the final stable alkene product, we have to lose an H plus ion. We regenerate the acid catalyst. And so we have an arrow that starts from a CH bond on the carbon atom next to where the OH group was, starting from that, and now our arrow ends in between the 2 carbon atoms. It doesn't go to the positive charge, even though our carbon is electron deficient. We don't draw it ending at the positive charge, we draw it ending between the 2 carbon atoms because we need to form a double bond, we need to form a pi bond. And if you've seen the alkene videos, remember that a pi bond is formed from 2 unpaired electrons in p orbitals. We need an unpaired electron on the carbon and an unpaired electron on the other carbon to form a pi bond in p orbitals. And so we have 2 electrons in our CH bond. One goes to the carbon that it's already attached to in a p orbital, the other goes to the other carbon. And this produces our alkene, and we've regenerated our sulfuric acid catalyst in this case, and we've eliminated water. Now, if you have longer alcohols, then we have to be careful where we do this dehydration because we may end up with a mixture of products being formed because there's different hydrogen atoms that we can essentially take to do this, this dehydration reaction. So if we take an example such as butan-2-ol, in any case where we have our OH group that's not exactly in the middle of the chain, we're going to be able to have these isomeric products. And so we can lose the water either by using the red hydrogen atom on the right, an arrow going from our CH bond to the CC bond to show the formation of double bond, and then our carbon then has too many bonds, so we have to kick off the OH group, an arrow starting at the CO bond and ending up at the oxygen. Or we can take the blue hydrogen on the left-hand side and do exactly the same, arrow pushing. If we take the red hydrogen, our alkene ends up being at the start of the chain, and so this ends up being but-1-ene. If we take the hydrogen atom that's at the blue hydrogen atom on the left-hand side, well now our alkene double bond ends up being in the middle of the chain, so butene, but also because we have these two heavier groups, the CH3s compared to the hydrogens, they can either be both on the bottom side or top side of the alkene, or on opposite sides of the alkene, above and below. So this is an example where we can form our EZ isomerization, stereo isomerization. So, time to have a go at some questions. So pause the video and have a go, and the answers will be on the next slide. You need to state the products and reaction conditions for when propan 1-ol and propan 2-ol are oxidized. Write the balanced equation for the reaction between butanol and Tollens reagent when we heat, and draw out the product, and what would it be with butanone. And then finally, what are the possible products of dehydrating pentan 2-ol? So the first question was to state the products and the reaction conditions. So we're oxidizing, so we need to use acidified potassium dichromate, and we can either write it as H2SO4 / K2Cr2O7 or as H+ / Cr2O7 2-. So either as the full molecules or as just the kind of ionic bits that matter. If we take propan 1-ol, it's a primary alcohol, so we know that we can sort of partially oxidize it by distilling it using dilute acid and excess alcohol up to the aldehyde, propanal, or we can oxidize it all the way up to the carboxylic acid by doing reflux, concentrated acid, and an excess of the oxidizing agent. For propan 2-ol, it's a secondary alcohol, so we know that we can oxidize secondary alcohols up, typically just using reflux to propanone, the ketone, but that we can't go any further because we now don't have any more available CH bonds. We have to break the CC bond, which means it's not easily oxidized. The second question was to draw out the reaction between butanol and our Tollens reagent. Now the equations that I put on the slide when we talked about it was the full proper equation. Typically for A level you can just, if we're representing an oxidizing agent, we can just use O in square brackets like we did for the potassium dichromate. And so we have our reaction, we have our butanol, CH3, CH2, CH2, CHO. Remember that aldehydes are CHO. React it with this O, and then we form CH3, CH2, CH2, COOH. That's already balanced, we don't have to do anything to it. And of course this would mean that we have our silver mirror. We would have seen our Tollens reagent been reduced down to metallic silver. With butanone, we'd have no reaction because that is a ketone and then can't be further oxidized up to the carboxylic acid. And drawing out the displayed formula, remember that displayed formula means that we draw out every single bond. So we have our CH3 group, our CH2 group, our CH2 group, and then we have our carboxylic acid group, which is our C, double bond O, and then an OH group. And then finally, we had to talk about dehydrating pentan 2-ol. Again, we're in a case of where the OH group isn't in exactly the middle of the chain, and so we're going to get a mix of isomeric products. We can take the hydrogen atom on the right of the OH group, which is shaded here in blue. By doing that elimination, I've not drawn the curly arrows, the mechanism for it, but by doing that dehydration, we'd end up with pent-1-ene. Again, if you've not seen the alkene video already, there's no EZ isomerization possible for this type of pent-1-ene because we have two hydrogen atoms attached to the same carbon, the one on the right. Or we could dehydrate using the hydrogen atom that's on the left of the OH group, circled in green. Our double bond now ends up being more towards the middle of the chain, and so we have pent-2-ene. But because we now have two heavier groups, we have this CH2-CH3 group and a CH3 group, we can have EZ isomerization. And if you're not happy with EZ isomerization, I'd recommend you watch my alkene set of videos. But we can end up with Z pent-2-ene, where we have those two heavy groups both above the plane of the alkene, and we have E pent-2-ene, where we have one group above and one group below. And so this is an example of stereoisomers, and the actual dehydration, the fact that we can dehydrate from different positions, is something that we call regioselectivity. So thank you for watching. You can find many more videos like this on my YouTube channel. If you found this video helpful, please leave a review on one of my tuition websites. I offer online tuition for chemistry, so please check the tuition pages for prices and how to contact me if you're interested in that. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.